A quiet flight test has just reshaped what unmanned aircraft can realistically do. For the first time, two drones successfully refueled each other in midair without any human control, even while flying fast and facing harsh lighting conditions. This video explains how that was achieved, why it removes a long-standing limitation on autonomous flight, and what this breakthrough reveals about the future of long-endurance unmanned aviation. Autonomous aerial refueling matters because it removes the most stubborn limitation on unmanned aircraft: how long they can stay in the air. Until now, endurance has defined the ceiling of what drones could realistically achieve. No matter how advanced their sensors or autonomy became, fuel eventually forced them to return, pause, or rely on human-controlled support. This new demonstration shows that the limitation is starting to disappear, reshaping how endurance is planned, measured, and extended over time. Researchers at Northwestern Polytechnical University confirmed that two unmanned aircraft completed probe and drogue refueling without human intervention. One aircraft acted as the tanker, while the other autonomously approached, aligned, and docked during formation flight. This was not a remote-controlled maneuver or a pre-programmed path-following exercise. The receiving aircraft independently made real-time decisions throughout the process, adjusting continuously to motion, distance, and alignment changes. What elevates this result is the environment. The test was designed to reflect operational stress rather than ideal conditions. The system functioned under direct sunlight, glare, uneven illumination, and partial visual obstruction. These factors often cause autonomous systems to fail, especially when precision is required. Despite this, the researchers reported a detection success rate above 99% and positioning accuracy down to the centimeter scale, demonstrating consistency rather than isolated success. This matters because endurance is not just about range. It affects planning, flexibility, and continuity. An aircraft that can remain airborne longer can observe longer, reposition more freely, and operate without frequent interruptions. It also marks a shift in trust. Autonomous systems are often evaluated based on what they can do in controlled environments. This test demonstrates reliability under uncertainty. That reliability is what allows autonomy to scale from experimental demonstrations into real operational frameworks, where unpredictability is the norm. The most remarkable aspect of this achievement lies in how it was accomplished. The system depended entirely on onboard perception and artificial intelligence. This design choice reveals a new level of confidence in autonomous decision-making. The receiving aircraft was equipped with a dual near-infrared camera system positioned to observe the tanker's drogue. The drogue itself carried 8 near-infrared LED markers, specifically arranged to create a recognizable spatial pattern. Using deep learning algorithms, the receiving aircraft continuously detected the drogue, filtered out background noise, and calculated its precise relative position in real time. What distinguishes this system is its resilience. The researchers intentionally tested conditions where visual data was incomplete. Even when 2 LED markers were obscured, the system maintained accurate tracking. This shows the model was not simply matching images, but interpreting spatial relationships. In practical terms, it was understanding where the drogue should be, not just where it appeared to be in a single frame. Near-infrared sensing played a critical role. By operating outside the visible spectrum, the system reduced sensitivity to glare and shadow transitions. Combined with AI-based interpretation, this allowed the aircraft to maintain stable perception even when lighting conditions changed rapidly. This is essential in real flight environments, where lighting can shift dramatically within seconds. Equally important is what the system did not rely on. There was no satellite positioning guidance used during docking, no external control input, and no human corrections. Every adjustment during approach and connection was made autonomously. This is a key indicator of maturity, because autonomy is only meaningful when it can operate independently at the most demanding moments. The reported performance metrics underscore this maturity. A detection success rate above 99% suggests reliability, while centimeter-level positioning accuracy demonstrates precision. Refueling requires both. A system that is accurate but inconsistent cannot be trusted, and a system that is consistent but imprecise cannot safely connect. By achieving both under challenging conditions, the researchers demonstrated more than a refueling technique. They demonstrated robust airborne perception. The broader implications of autonomous refueling become clearer when connected to real unmanned platforms. One example is Geotion, a long-range unmanned aircraft that recently completed its maiden flight. Publicly available information places its official range at around 7,000 kilometers. On its own, that defines a fixed operational boundary. With in-flight refueling, that boundary becomes adjustable. Autonomous refueling does not simply extend distance. It changes how endurance is planned. Instead of operating in isolated flight segments, unmanned aircraft can operate in stages, supported by mobile refueling assets that do not require human pilots. This enables longer airborne presence, flexible repositioning, and sustained operations without increasing fleet size. It also supports more efficient maintenance cycles, improved energy planning, and smarter use of onboard sensors. Another key shift lies in system design. When refueling is autonomous, unmanned aircraft can support each other rather than depend on separate, human-operated platforms. This creates distributed networks instead of linear support chains. In such networks, endurance is shared rather than centralized, improving resilience and adaptability. It is useful to contrast this approach with existing refueling drones such as the MQ-25 Stingray, which focuses on supporting crewed aviation. That model extends human flight time. The approach demonstrated here extends unmanned autonomy. Both are valuable, but they serve different long-term visions. Importantly, autonomous refueling does not eliminate constraints. Tanker availability, coordination complexity, and airspace management still matter. However, autonomy significantly reduces the human workload associated with these challenges, allowing systems to operate with greater independence. What ultimately changes is not just capability, but continuity. Unmanned aircraft are no longer bound to short operational windows. They become platforms capable of sustained presence. That shift influences everything from design priorities to operational planning. This is why autonomous refueling is best understood as an enabling layer. It unlocks potential that already existed but could not be fully used. Once endurance becomes flexible, unmanned aviation enters a new phase defined by persistence rather than limitation. This achievement marks a subtle yet meaningful turning point in autonomous aviation. By demonstrating that unmanned aircraft can refuel each other reliably under demanding conditions, researchers have removed a long-standing constraint on endurance. The significance is not spectacle, but confidence in perception, decision-making, and machine-to-machine coordination. As autonomy continues to mature, endurance will no longer define what unmanned aircraft cannot do. Instead, persistence will shape how these systems are designed, deployed, and evaluated over time. This shift redefines long-duration flight, opening possibilities for continuous operations, planning, and sustained presence across aerospace applications. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Also, you can visit our website, SpaceEyeNews.com. Thank you for watching, and see you next time.